The discovery of ancient galaxies that seemingly predate the universe has forced astronomers to revisit the very methods they rely on to measure cosmic time and distance. At the heart of these calculations lies a concept that is as elegant as it is critical: redshift. To understand how we can say a galaxy is 13 billion light-years away, or that it existed just 300 million years after the Big Bang, we must first understand how light behaves as the universe expands. When a galaxy emits light, that light begins a journey across the fabric of space. But unlike a beam traveling through a static vacuum, space itself is stretching, and as it stretches, it also stretches the light traveling through it. This causes the light's wavelength to increase, shifting it toward the red end of the electromagnetic spectrum, a phenomenon known as cosmological redshift. The greater the redshift, the farther the galaxy. The farther the galaxy, the deeper into the past we are looking. It's a beautiful system, but it's not flawless. Redshift is the backbone of our cosmic distance ladder. Using it, astronomers can calculate how much the universe has expanded since the light left a galaxy. The James Webb Space Telescope excels at detecting infrared light, the kind of stretched, red-shifted light emitted by very distant, ancient objects. That's why JWST has been able to peer further into the early universe than any observatory before it. But interpreting redshift isn't as simple as reading a number off a gauge. There are two primary ways redshift is determined: photometric redshift and spectroscopic redshift. Photometric redshift is faster. It estimates redshift by analyzing a galaxy's brightness through various filters. Think of it like trying to determine the age of a wine by looking at its color through tinted glass. It can be surprisingly accurate, but it's also prone to errors, especially with very distant objects. Dust, unusual star populations, and even gravitational lensing can throw off readings. Spectroscopic redshift, on the other hand, is the gold standard. It involves splitting a galaxy's light into its component colors and analyzing specific absorption or emission lines, unique fingerprints of elements like hydrogen or oxygen. By measuring how far these lines have shifted, astronomers can determine redshift with incredible precision. Many of the early impossible galaxies detected by Webb were initially measured using photometric redshift. That led some skeptics to question the findings. Could these objects be closer than we thought? Could dust or interference be tricking our instruments? To answer those concerns, follow-up observations with spectroscopic methods began, and the results were stunning. One by one, the redshifts were confirmed. These galaxies truly were as distant and as ancient as the original measurements claimed. Glass Z13, Sears 1749, and others have now become case studies in the reliability of Webb's vision. But these confirmations also deepened the mystery. Because now there was no escape hatch. We couldn't blame faulty instruments or bad math. The galaxies are real, and their existence is rewriting the physics of early cosmic evolution. This has triggered a renewed emphasis on refining our models of redshift and expansion. Scientists are now incorporating variables like early universe conditions, feedback from primordial black holes, and non-uniform inflation into simulations to see if any could produce galaxies of such mass so soon after the Big Bang. It's also reignited interest in alternative cosmologies. Could our interpretation of redshift itself be incomplete? Some theories, though controversial, suggest that what we perceive as redshift might be influenced by unknown quantum effects or interactions with dark energy fields that vary across space-time. Others suggest that light might be aging or losing energy in ways we don't yet understand. A modern revisit of the once-dismissed tired light hypothesis. While most mainstream cosmologists remain skeptical, These fringe ideas are receiving more attention as data from JWST continues to challenge conventional wisdom. What's certain is this: Redshift is not just a technical detail. It's the cornerstone of how we measure, date, and understand the universe. And now, it's at the center of a cosmic puzzle that may reshape everything we thought we knew. At Infinity Beyond, we're here to follow that light, however faint, however redshifted, to its final answer. In our next segment, we'll explore what these revelations mean for our understanding of dark matter and dark energy. Could the early emergence of massive galaxies point to a hidden form of matter? Or are we on the cusp of discovering an entirely new force that governs the infant universe? The cosmos is whispering its secrets, and we're finally learning how to listen.